Here's another book problem that I want to go ahead and do a detailed solution to. Graphing this function x times e to the minus x squared using the help of calculus. So let's do some bullet points here. Symmetry. That's what I always start with. Symmetry. And, well, there's no periodicity because there's no sine or cosine or anything like that. But we can check for even and odd. So we plug in minus x. We get minus x e to the minus quantity minus x all squared. Careful with your minuses. The minus in front certainly comes out, and the minus inside the square just goes away. Well, that's exactly minus f of x. And so that's an odd function. Not an off function, an odd function. So that's good. It means that we only have to do, we have to graph on 0 to infinity. You know, I don't want to close bracket there. 0 to infinity on the right hand side of the line, and then we're just going to revolve it, rotate it around the origin. Okay. While we're at it, let's talk about domain, continuity, etc. Well, there's no number that's illegal to put into here. The domain is everything. It's take a polynomial, put it into an exponential, multiply it by a polynomial. It's perfectly continuous and differentiable. So, easiest way to summarize that is it's differentiable everywhere. So it's certainly continuous and then hence certainly defined everywhere on the whole real line. So there's no weirdness about that. So that right away tells us that there's, if we look at sort of the infinities category, there's no vertical asymptotes because there's no discontinuities of any kind. But we can look for horizontal asymptotes, or in general end behavior, by looking at the limit as x goes to infinity of x e to the minus x squared. Okay. Well, let's see what happens with that. Okay. This is, to make it maybe a little more obvious, x goes to infinity of x over e to the x squared. And a lot of people would use L'Hopital's rule for this problem. I don't think that. I think it's an overkill. The thing that we know about exponentials that you can easily convince yourself of numerically, or you can prove with L'Hopital's rule, is that exponentials kill polynomials all the time. Now the question is, we've got e to the x squared. Does that make it bigger or smaller? Well, as soon as x gets past 1, x squared is going to grow faster than x, and so e to the x squared is going to grow faster than e to the x. So we can make that more precise by just saying that that is less than whatever the heck it is. It's less than what you would get if you just have x over e to the x. That's an x, sorry. Because this makes it the denominator bigger, and therefore the whole fraction is smaller, and therefore the limit's going to be smaller. Okay. Everything here is a positive number, so we don't have to worry about flipping the order of any inequality. So let me just put a 0 less than right at the start. Everything here is positive, because x is positive, e to anything is positive. And this is one of the fundamental limits that we just remember. If you compare x and e to the x wins. And since e to the x is going to infinity, 1 over e to the x wants to go to 0, and it wins, and so the limit is 0. So yes, you could do that L'Hopital's rule, but as long as you just know your basic facts about comparing polynomials and exponentials, L'Hopital's isn't really essential. Okay, so that's 0, so that's a horizontal asymptote. So yes, we're getting a horizontal asymptote. I'll bold that and put the question mark. Horizontal asymptote, I'm not, y equals 0. Okay, in other words, the x-axis. Alrighty. So now that's interesting stuff to know. What about derivatives? Let's do those. And some people were commenting that those get maybe a little bit hairy, and they do. Okay, so it's the derivative of this. They got the product rule. So derivative of x is 1 times e to the minus x squared left alone, plus x left alone times the derivative of e to the minus x squared. That's itself, but then times the chain rule. Okay, now, looks scary, isn't. Because the e to the minus x squared factors out, and I get a 1 minus 2x squared. And I'm going to set that equal to 0. e to anything is never ever equal to 0, and so that doesn't really matter. The only possibility is that 2x squared is equal to 1, and so x squared is 1/2, and so x is plus or minus 1 over root 2. The plus or minus is not too surprising because, again, the symmetry, it's an odd function. We're going to find, if we find a max or min on one side, we're going to find the opposite, min or max, on the other from rotating it around. Okay, so that's where the first derivative is equal to 0. Now what about f double prime? Okay, so let's go back to here. Product rule again. Derivative of the first, that's that minus 2x e to the minus x squared times the second part left alone. Oh, this is looking frightening, but it's going to be okay. Now we differentiate that second part, and we just get a minus 4x. Okay, looks messy, but again, let's factor out the common factor. And what else do we get? We get a minus 2x plus 4x cubed from combining these guys, and then minus 4x, and that actually combines pretty nicely. And even an x factors out again. So there's an x there. And then minus 2 and minus 4 is a minus 6, plus 4x, and it's x squared because I factored out an x. Set that equal to 0. So again, e to the minus x squared cannot equal 0, so it just doesn't matter. You can think of it as just, you could divide it out, for example. That's one way to think about it. So either x equals 0, or 4x squared equals 6, which leads to x equals plus or minus square root of 2/3. Okay, which is, and this was the square root of 1/2, if you want to write it that way, just for consistency. So this is a little bit past that. These two other inflection points that aren't at x equals 0, excuse me, are going to be past that. Okay. Oh, and you know what I forgot? Before doing derivatives, I usually do intercepts, and I just totally blew by that. Let me go back to that. It's really easy. That's the first place we can observe this phenomenon of setting something involving e to the minus x squared equal to 0. E to the minus x squared itself can't vanish, but x can, and so that's just going to be where x equals 0. So like the previous example that I was doing, this thing goes through the origin. Okay. And at the origin, we have a 0 the second derivative, possibly an inflection point. We have to check the sign chart carefully. And then there's two other zeros for the second derivative and two zeros for the first derivative. So let's make our master chart of interesting points we would like to plot. And we'll just do it in this form. Okay. And then we're going to need to have some sign information as well. But let's just go ahead and start this one. X and y. Okay, we know that 0 is interesting and y is equal to 0 there. We already knew that. Okay. And it goes to the origin. And then the next interesting point for plus is root 1/2. Okay. And then we're going to have to plug in y. Let's do some scratch calculation here. F of root 1/2 is going to be root 1/2 times e to the minus, and then square root 1/2, where that's 1/2. All right, let's get a numerical value on that. About 0.4. And what the heck, let's just go ahead and remind ourselves the numerical value of this guy. That's about 0.7. Okay, so we could plot that by hand. And then the next one is root 2/3, which is approximately, I don't know that off the top of my head. That's 0.8. I'm doing it very roughly because, after all, this is just for a sketch. And then we have to plug that in. F of root 2/3 equals root 2/3 e to the minus 2/3. Plug that sucker in. And about 0.4. That's a little suspicious. That's going to be That's actually rather suspicious. What's going on there? They're pretty close. They should be pretty close, but this guy should be bigger. Let's see. Do I trust the computer here? Oh, that was 4-3. Oh, I see. I was just reading them in the wrong order. They are pretty close. Okay, so and then this one is the 419. Okay. So this is about 4-3, and this is about 4-2. It's really quite close to each other. That's interesting. I didn't know they were so close. But I think that is accurate. Okay, so those are the interesting points to plot. We still need some sign information to figure out how those connect well. Oh, and then let's put in, sorry, I just x took out a row, but x going to plus infinity, then y goes to 0. And what is it? Well, when x is positive, one thing I didn't do here, when x is positive, then this quantity is positive. So let me write that down. If x is positive, then y is positive. I usually, when I do the intercepts, I usually go ahead and like to think about the signs as well, and I just kind of skipped over that. So on the entire region that we're going to plot first, the right-hand side of the line, it's always positive. And so this intercept is coming to 0 from above, from the plus side. Okay, so that's some points to plot, and now we just need to go back to those derivatives and be a little more careful about the signs of what's happening. If x, let's insert a little chart here. Okay, I don't think I'll need so many rows. Okay, so x and f prime of x, make a sign chart for that. When x is 0, x is less than root 1/2, what's going to happen? This is always positive, so it can't affect the sign. If x is less than root 1/2, well, and that simple number to put in there is 0, for example, then this part dies, and we just get 1. So that's positive. When x equals root 1/2, of course, that's where it's 0. And then when x is bigger than root 1/2, that's where x squared is bigger than 1/2, or 2x squared is bigger than 1, and so that's going to be where this becomes negative. Okay, so that's the sign chart for the first derivative. Sign chart for the second derivative is a little more complicated, but not too hard. Let's put in a table. Probably don't need quite so many rows. So here's x and f double prime of x. Okay, when x is 0, now that was a 0. That is interesting. Okay, and if x is between 0 and root 2/3, then we have to plug that into here. Okay, so x is positive. Anything is positive. X is, let's say it's a very small number, just past 0. This is going to be small, and so this is going to be negative. Concave down. Okay. X equals root 2/3. Whoops. Didn't mean to do that. X equals root 2/3. That's where it's 0 again. And then x greater than root 2/3. What happens? Well, these guys are still both positive, but here that's where this guy takes off, and that dominates this guy, and that's going to be positive. Okay. So using that information, it starts out concave down, and as it's going through that maximum, because root 1/2 is before root 2/3, plus 0 minus. That's a max. Let's check that with the second derivative test. Yeah, the second derivative is negative there, so it should work. And then it goes through another inflection point and then to an asymptote. Okay, so now let's do the little bit of a cheating part since I'm on the computer, and actually just take x e to the minus x squared. So we have something to look at. Okay, and that window's pretty good. Okay, so we would plot by hand. We would plot 0, 0. We'd plot the maximum, which is about 0.7, 0.43, and then the inflection point, which is down here. You know, that calculation I had, this calculation of the the y value for the inflection point cannot be right. It's got to be more like it's got to be in here. So I think I did something a little wrong with that. I don't want to redo the whole video, but don't trust these values. I don't want to go back and fix the arithmetic. But we do get one inflection point up here, and oh, I know what it is. That's a 3/2. Well, that's easy to fix. I bet you guys all were screaming at me and saying, that's a 3/2. 6/4 is 3/2. Okay, that makes more sense. I'll fix it. I did that on purpose, I swear, to get you guys to see that. Okay. There we go. So now let's go ahead and do a little scratch calculation here. Root 3/2. That makes so much more sense. E to the minus 3/2. And numerical. There we go. Ah, okay. 0.27. I thought that 0.42 was just bogus, but didn't want to admit it. Okay, so now... Okay. Now here's our graph. So that's root 3/2 and about 0.27. So starting at 0, going up, concave down, then maxing out, and then switching to concave up, and then having an asymptote over here. So that's what we would graph first. 1, 2, 3 points and an asymptote. Connect the dots based on the derivatives, and then rotate. And then so that's going to go down, minimum, up over here. Okay. It's a lot of work, there's no doubt about it. But it's a great way to really master all these tools and feel like you have the power to understand functions yourself without trusting the magic box.